On September 5th, 2017, a scientific instrument sitting more than 12 billion miles from Earth began picking up something that, according to every physical model built to describe that part of space, wasn't supposed to be there. Not a single spike. Not a brief pulse that could be dismissed as sensor noise. A steady, continuous hum embedded in the plasma of interstellar space itself, and it hasn't stopped since. 9 years later, in 2026, NASA and the scientists who study this data still can't say for certain what's actually producing it. That instrument belongs to Voyager 1, the oldest continuously operating spacecraft humanity has ever built, and what it detected in the space beyond our solar system remains one of the most genuinely unresolved puzzles in modern astrophysics. This is the story of that persistent, unexplained signal, how Voyager 1 came to be in a position to detect it in the first place, and what NASA's own published research says, in plain terms, about how far scientists still are from fully understanding what it means. To understand why this finding carries so much weight, you first have to understand exactly where Voyager 1 is, how it got there, and why no other instrument in human history has ever been positioned to make this particular kind of measurement before. Voyager 1 launched on September 5th, 1977 from Kennedy Space Center in Florida, on a mission that was originally supposed to be almost modest by comparison to what eventually happened. Fly past Jupiter, fly past Saturn, take photographs, gather data, and then, according to NASA's own original planning, fade quietly into retirement sometime around 1981. Nobody involved in building the spacecraft was under any illusion that it would still be transmitting data back to Earth nearly 50 years later. But Voyager 1 kept going. It used the gravity of Jupiter and Saturn the way a slingshot uses tension, gaining speed with each flyby, and by the late 1980s, it had already become the most distant human-made object ever launched into space. Then, in August of 2012, 35 years after launch, it crossed a boundary called the heliopause, the point where the sun's own outward stream of charged particles, the solar wind, finally loses its strength against the pressure of the interstellar medium pushing back from the other side. Everything inside that boundary belongs, in a very real sense, to our solar system. Everything outside it belongs to something else entirely. Voyager 1 crossed that line and kept transmitting from the far side, becoming the first spacecraft in history to physically leave the solar system and continue speaking to us from beyond it. That achievement alone would have secured Voyager 1's place in the history of space exploration. What happened next in the years following that crossing is the part of the story that matters most here, because it's what turned Voyager 1 from a historic milestone into an active, ongoing scientific mystery. Since 2012, Voyager 1 has been sending back direct, first-hand measurements of what interstellar space actually looks like from the inside, not modeled from a telescope on Earth, not calculated from theory, but recorded directly by an instrument physically present in that environment. And what it began finding, starting 5 years after that crossing, didn't match what decades of careful, peer-reviewed modeling had predicted it should find. Here's the background necessary to understand why that mismatch mattered so much to the scientists studying it. For decades before Voyager 1 ever reached the heliopause, physicists built detailed mathematical models describing what interstellar space should be like, based on everything we understood about how charged particles, magnetic fields, and plasma behave at the extraordinarily low densities found between star systems. The general expectation across most of that modeling was that this region should be relatively calm, thin, cold, and largely undisturbed, a quiet transitional zone between one star system and the vast emptiness separating it from the next. Starting on September 5th, 2017, Voyager 1's plasma wave subsystem, an instrument specifically designed to detect oscillations and waves moving through the surrounding plasma, began picking up something that didn't fit that quiet picture at all. According to the peer-reviewed research that eventually followed, the instrument recorded a persistent, narrow-band emission, essentially a steady, continuous tone embedded in the plasma surrounding the spacecraft, one that showed no sign of fading or disappearing the way a single, brief event would. Researchers who study Voyager 1's plasma wave data have continued tracking this emission in the years since, and it has now been recorded continuously across a stretch of interstellar space spanning more than 900 million miles, roughly 10 times the distance between the Earth and the Sun. That's not the kind of finding that gets dismissed as a glitch or a one-time anomaly. A signal detected consistently across nearly a decade, across hundreds of millions of miles of travel, is a genuine physical phenomenon, one that needed an explanation grounded in real physics. The problem was, and still is, that scientists have narrowed the possible explanations down to two genuinely different physical mechanisms, and as of the most recent published research, they still can't determine with confidence which one is actually correct. The first possible explanation involves something called thermally excited plasma oscillation, essentially the natural, ordinary vibration of charged particles interacting with each other and with their surrounding environment. If this explanation turns out to be correct, it would still represent a genuinely significant scientific finding, confirming that interstellar plasma carries this kind of persistent internal activity in a way nobody had directly measured before Voyager 1 arrived. But it would fit within existing physical frameworks without requiring scientists to fundamentally revise how they think plasma in interstellar space actually behaves. The second possible explanation is something considerably more disruptive to existing theory, a phenomenon called quasi-thermal noise. This is a distinct physical mechanism, one that would carry information about the density and temperature of interstellar plasma in a subtly but importantly different way than ordinary thermal oscillation does. If Voyager 1's persistent signal turns out to be quasi-thermal noise rather than simple thermal oscillation, it would mean existing models of the interstellar medium, the physical description scientists have built over decades to explain how plasma behaves in the space between stars, would need real, substantive revision to account for it. Telling these two possibilities apart isn't simply a matter of looking more closely at the same data Voyager 1 has already sent back. It requires either additional measurements from Voyager 1 itself, which becomes an increasingly difficult proposition every year as more of the spacecraft's instruments are shut down to conserve its rapidly dwindling power supply, or an entirely new mission, specifically designed and built to study interstellar space with instruments capable of making the more detailed measurements needed to finally settle the question. As of 2026, no such mission currently exists, and none is currently funded. According to researchers who have studied this problem directly, if a new interstellar mission were designed, funded, and launched starting today, it wouldn't reach the heliopause and begin making comparable measurements for at least another 25 years, which means that whatever the true answer to this specific mystery turns out to be, Voyager 1's own data may remain the closest thing scientists have to a direct answer for a very long time to come, possibly for the rest of most researchers' careers. That persistent hum isn't the only piece of Voyager 1's interstellar data that has forced scientists to revise their expectations. Two other findings, both confirmed through direct measurement rather than indirect modeling, add real weight to the broader picture of just how different the actual environment beyond our solar system turned out to be from what decades of theoretical work had predicted. The first involves temperature, and it's the kind of finding that sounds almost contradictory until you understand the underlying physics carefully. Instruments on Voyager 1, and later confirmed by its twin, Voyager 2, recorded plasma temperatures at the heliopause boundary itself somewhere between 30,000 and 50,000 Kelvin, comparable to conditions found near the surface of certain stars. Some researchers and science writers have taken to calling this region, informally, a wall of fire. A vivid description, but one that requires careful, honest explanation rather than being taken at face value. There's no combustion happening in that region, nothing burning in any conventional sense. Temperature in physics is fundamentally a measurement of how fast individual particles are moving, not a measurement of how much heat those particles are capable of transferring to something sitting among them. Because this particular region of space is so extraordinarily sparse, with particles spread thin across billions of miles, there simply aren't enough of them colliding with anything to transfer meaningful heat. Voyager 1 passed directly through a measured plasma temperature that would vaporize almost anything on Earth, and its 1970s-era electronics didn't register so much as a change in operating temperature because there was nearly nothing there to physically touch it. The second finding involves magnetism, and it directly connects to a broader question about how sealed off, or how connected, our solar system actually is to the rest of the galaxy. Before Voyager 1 reached the heliopause, one of the standard theoretical predictions was that the magnetic field environment on either side of that boundary should be dramatically different. Inside the bubble, the sun's own magnetic field, carried outward by the solar wind. Outside, a completely separate magnetic field generated by the broader structure of the galaxy itself. Two distinct systems, from two entirely different sources, expected to diverge sharply right at the point of crossing. Voyager 1's magnetometer recorded something different. The magnetic field just beyond the heliopause appeared to point in almost the same direction as the field inside it, an alignment that, with only one spacecraft's worth of data, researchers initially couldn't be certain was a genuine pattern rather than a coincidence tied to Voyager 1's specific location along an enormous, irregularly shaped boundary. When Voyager 2 crossed the heliopause 6 years later in 2018, at a completely different location on the opposite side of the solar system, its own magnetometer recorded the same alignment. NASA's own science communications team described this directly, noting that the Voyager 2 observation confirmed what had initially looked like a surprising, possibly coincidental result from its twin. Two magnetic fields from two entirely different sources sitting in close agreement with each other at the true edge of everything we call home, a finding that still doesn't have a fully settled theoretical explanation, and one that suggests our solar system isn't as magnetically isolated from the rest of the galaxy as earlier models had assumed. All three of these findings, the persistent, still unexplained plasma hum, The extreme but harmless temperatures at the boundary itself, and the unexpectedly aligned magnetic fields on either side of it, share a common thread. Each one represents something that decades of careful, peer-reviewed theoretical modeling failed to predict. And each one was only discovered because a single aging spacecraft happened to survive long enough and travel far enough to actually measure that environment directly, rather than relying on inference from a telescope or calculation performed from the comfort of a planet safely tucked inside the solar system's own protective bubble. It's worth being direct and precise about why this specific combination of findings matters beyond simple scientific curiosity. The heliopause isn't just an abstract boundary line on a diagram. It functions as a genuine shield, deflecting a significant portion of the high-energy cosmic radiation that streams in from distant, long-exploded stars scattered across the galaxy. Radiation that would otherwise reach the inner solar system, including Earth, at considerably higher intensity. If the environment pressing against that shield from the outside is genuinely more turbulent, more energetic, and more magnetically connected to our own solar system than earlier models assumed, that has real implications for understanding how stable and how effective that protective shield actually is over long geological timescales, a question that matters directly for understanding the conditions life on Earth has experienced, and will continue to experience, over the deep span of our planet's history. None of that means anything is currently at risk, and it's important to be clear about that distinction rather than letting the science drift into unwarranted alarm. What it does mean is that a fundamental piece of the physical picture protecting our solar system turns out to be considerably less well understood than researchers assumed before Voyager 1 actually got there and started measuring it directly. That's precisely the kind of finding that legitimately deserves to be called something scientists can't explain, not because it's frightening, but because it genuinely, honestly isn't resolved yet, according to the researchers who've spent years studying the data. All of this context brings us directly to what's actually happening with Voyager 1 right now in 2026, and why the timing of this entire situation carries a particular kind of urgency that wasn't present even a few years ago. Voyager 1 runs on a radioisotope thermoelectric generator, a sealed device that converts the heat produced by decaying plutonium into electricity. At launch, it produced roughly 470 watts. Nearly 49 years later, it produces a small fraction of that, and loses about 4 watts of capacity every single year, permanently, with no possibility of refueling or replacement. On February 27, 2026, during a routine, planned calibration roll, a standard maneuver the mission team has executed many times over the decades, Voyager 1's power levels dropped further than engineers expected. Rather than risk letting the spacecraft's automatic safety systems handle the situation on their own, a process that would have meant an uncertain recovery stretched across a communication delay of more than 23 hours in each direction, the team at NASA's Jet Propulsion Laboratory made a deliberate, difficult decision. On April 17, 2026, they sent the command to permanently shut down the low-energy charged particles instrument, a device that had operated almost continuously since Voyager 1's launch in 1977, nearly 49 uninterrupted years of service, according to NASA's own published description of the shutdown. Of the 10 identical sets of instruments the spacecraft originally launched with, 7 have now been permanently retired. That leaves Voyager 1 with a shrinking set of tools still capable of studying exactly the kind of interstellar phenomena described throughout this story, including the plasma wave instrument responsible for detecting that still unexplained persistent hum in the first place. Every additional instrument lost represents a permanent, irreversible reduction in the spacecraft's ability to keep gathering the kind of data that might eventually help resolve this ongoing mystery. But the team hasn't given up on buying more time. Engineers at JPL are currently testing an experimental power restructuring procedure, nicknamed internally the Big Bang, designed to recover small amounts of electrical capacity currently being lost to inefficiency in the spacecraft's aging systems. Because any change to hardware this old carries genuine risk, the team chose to test the procedure first on Voyager 1's twin, Voyager 2, which currently has a slightly larger power margin, making a failed attempt there less costly to the overall mission. Those tests were scheduled for May and June of 2026. If they succeed, the same fix will be attempted on Voyager 1 itself no earlier than July. And according to NASA's own published statement on the plan, if it works, there's even a chance that Voyager 1's shutdown instrument could be switched back on. There's also a specific, already confirmed milestone sitting on the calendar, one that will arrive regardless of how that repair attempt goes. According to NASA's own tracking data, on Wednesday, November 18th, 2026, at 2:16:07 a.m. Pacific Time, Voyager 1 will reach a distance of exactly 799,96 miles from Earth, the distance light itself travels in a full 24 hours, making it the first human-made object in history to reach that specific threshold while still transmitting data home. At that distance, sending a single command and receiving a response takes nearly 2 full days round trip, an operating reality that makes every diagnostic step in maintaining this aging spacecraft an exercise in extraordinary patience. Sitting all of this together, the historic crossing of the heliopause in 2012, the persistent, still unexplained plasma hum first detected in 2017, the extreme but harmless boundary temperatures, the unexpectedly aligned magnetic fields, and now, in 2026, an aging power supply forcing painful permanent decisions about which instruments survive and which go silent forever, paints a genuinely accurate picture of what NASA has actually confirmed in its own published research and its own official statements about what Voyager 1 detected out at the edge of everything, and how much of it remains, honestly, unresolved. It's worth being precise about what "can't explain" actually means in this context, because that precision separates an honest account of this story from an exaggerated one. It doesn't mean scientists are baffled in some dramatic, mysterious sense, unable to offer any explanation at all. It means researchers have narrowed the possibilities down to 2 specific, well-defined, physically plausible mechanisms: thermally excited plasma oscillation on one hand and quasi-thermal noise on the other, and currently lack the additional data needed to determine with confidence which one is actually responsible for what Voyager 1 keeps detecting year after year across an ever-widening stretch of interstellar space. That's not a failure of science. It's science working exactly the way it's supposed to, identifying a genuine anomaly, narrowing down the plausible explanations through careful analysis, and being honest about the fact that resolving the final question requires more data than currently exists, data that may not become available for another quarter century or more, unless some future mission is specifically designed and funded to gather it. There's something worth sitting with in the fact that this particular mystery, one of the more genuinely open questions in modern astrophysics, is being slowly, carefully investigated using data from a machine that predates the personal computer, running on hardware that would be considered primitive by nearly any modern standard, transmitting information across a gap so vast that even light itself takes the better part of a day to cross it. Voyager 1 wasn't built to solve this particular puzzle. It wasn't even built with interstellar space in mind at all. Its original mission ended, on paper, in the early 1980s, decades before it ever reached the boundary where this signal was eventually detected. And yet, because it kept working, because its plasma wave instrument survived long enough to still be functioning when the spacecraft finally crossed into a region of space no instrument had ever occupied before, it managed to hand scientists a genuine, still unresolved mystery about the fundamental nature of the material filling the space between the stars. That mystery is still unfolding right now, in real time, as Voyager 1 continues its outward journey, its remaining instruments slowly, one by one, being switched off to conserve a power supply that cannot be replenished. Its team at JPL working carefully, patiently, through an experimental repair attempt that might buy the mission a little more time to keep listening to that same persistent, unexplained signal a little longer. Whether scientists finally determine what the hum actually represents before Voyager 1's last instrument goes silent for good, sometime in the early 2030s according to current projections, remains an open question. Nobody, not the engineers, not the physicists studying the data, not NASA itself, can currently promise an answer to. If you want to follow how this mystery develops, and whether the upcoming repair attempt succeeds in keeping Voyager 1's remaining instruments alive long enough to gather more data, that story is still actively being written right now, 15 billion miles from where you're sitting. Subscribe if you'd like to keep following where it goes.